So, we start the I hope it's covered. So we had started to talk about rational and regular functions. So we'll just continue from where we are. So, so we had that x is an, say, defined variety. We have put the coordinate ring of x was ax, which was just the, so x is an, this was just the polynomials by the ideal of x, and then we had looked at the field of rational functions, ax, which was the fraction field. So elements are of the form f divided by g, with f and g are in ax, and g is not the zero function. And then, yeah, that is indeed. And so then we had defined the local ring at the point. So if P is a point in X, we have the local ring. This is the set of all elements in Ax, f divided by g, where I can choose this representation in such a way that g of P is different from 0. And so one can think of this rational function, this quotient of this rational function being defined at the point P. Because the denominator is not 0. And so then we had defined the ring of regular functions an open subset. These are just the rational functions which are defined everywhere. So O, this is the intersection of all points P in U of OXP. And so if I say that a rational function is defined at P, if it can be written in this form with g of P different from 0, this is just the same as the set of all f, the H in Kx. That's that H is defined at P. And as a last thing we had seen, so this is O, and note this as O of U, regular functions on U. And we had seen that, so if H is a regular function on U, then it defines indeed a function on U, so then H defines a function which I also call H on U. Okay, namely, I send a point P to what I would call H of P, which is f of P divided by g of P, for any fg such that H is in Kx equal to f divided by g, and g of P is non-zero. Okay, and we had seen that this is well defined. You also know, if you have if you think of it as like you do in school, you can take quotients of polynomials and can evaluate it by evaluating the numerator and denominator, making sure that the denominator does not vanish. Okay. So this was this definition. So this is also where we were. And conversely, if you have any rational function, it will always define a regular function on some open subset of X. So, definition that f, we will call it H, be an element of a rational function on X. The domain of F is what is called H, but there should be the domain of H, is the set of all points in X such that H lies in the local ring at P, so that it's defined there. And we can also, and we can see that this is an open subset, so the domain of H is a non-empty open subset of X, obviously in the heuristic topology, because I can write the domain of H to be the union over all G, I have to tell you which G's, of X minus the zero set of G, where G runs through all polynomials such that I can write H equal to the class in AX of F divided by G for some F. So because what this just says is the domain of H consists of all the points such that I can write H as a quotient of two polynomials such that the denominator does not vanish. No? Obviously for different points I might have to choose different representations. Okay, so and therefore it's obviously an open subset of X because it's the union of the complements of these. And it's also obviously, you can also easily see it's on empty. One should also say, so I have to call this thing the local ring at P. It has a property which one usually says the property of being a local ring. So we call, if I look at the local ring of P, now we had seen this was just the set of all, say, H in Kx, such that H is defined at P. And so it has there's an ideal here, so the maximum ideal these are all the elements in the local ring which vanish at P. So if I put P into this thing, I get 0. So this is, so let's say P is MP, which is the set of all H in OXP, such that H of P is equal to 0. No? H of P as before was I write H as F divided by G, such that G of P is non-zero. And then what this says is then in that case also in this, but then I get that F is 0. That's what I get. 0. Okay. So this is obviously an ideal because if And in fact, it's obviously a maximal ideal. Because it's the kernel of the evaluation homomorphism at P, as the kernel. I could write this as evaluation at P from OXP to K, where I just take an element here, so a rational function, and I evaluate it at P. This map is obviously surjective because this contains the K itself, and the kernel, so therefore the kernel is a maximal ideal. We have a homomorphism, surjective homomorphism to a field, and you can see something more, namely it is the unique maximal ideal. And more precisely, every element which does not lie in this ideal is invertible, is a unit. So, and so in some sense more strongly, and so it consists of all non-used units. Obviously, if you have a unit, then it cannot lie in an ideal except for the whole thing. So it follows in particular that this must be the unique maximal ideal. And so why is that? It's kind of obvious. So if H is an element in OXP without the maximal ideal, then we can write H equal to F divided by G, with G of P is different from 0, but also F of P is different from 0, because otherwise H of P would be 0. So thus, we can form H to the minus 1, which is G divided by F. And and clearly this still lies in OXP because the denominator is not 0. And so this element is invertible. So a ring with this property that it has a unique maximal ideal which consists of all non-units is called a local ring. And people study this. Very often you can kind of reduce looking at rings by looking at certain local rings. But the origin of the word local ring comes from this one, because this is this really is in some sense the local ring at P, because it describes the functions near the point P. Whereas AX maybe describes all the functions on X. This describes the functions which live near X, so it's the local ring, and you can kind of try to read off the local properties of X near P from this local ring. In fact, they are somehow encoded there. Okay, but we'll see that maybe later. Now I want to see one more thing. So I want to see that if we are on an affine variety, so a closed subset of an irreducible closed subset of a affine space, I could ask myself, I can look at the functions which are regular on the whole of this affine variety, and one could wonder whether these, whether we have defined something new. I mean, whether these are more than just the elements, the restrictions of polynomials. And the answer is no. If a if a function is regular on the whole of an affine variety, then it is actually an element of AX, so the restriction of a polynomial. Okay, so let me state this here, and that's kind of good to know that we haven't kind of increased things too much. So that in some sense it will mean that if you work with affine varieties, you can really work with polynomials. So the statement is the following proposition. Let X be an affine variety. So this means irreducible closed subset of some affine space. Then, if I take O of X, so these are the functions which are regular on the whole of X, this is just AX. So that's a non-trivial statement, because if you look at it, here it says I have a function which I can write for every point in X. I can write it as f divided by g, so that g of p is non-zero. Okay, but for different points I might have to take different such representations. But the claim is, if we have this, then in fact I can write it as f divided by 1 for f a polynomial. Okay, so it's kind of somewhat surprising. So if for every point I can find a denominator which doesn't vanish there, I can make the whole denominator go away. Okay, so let's see. Obviously this is not trivial. So clearly we have that AX is contained in OX, because I just can send the class of the function, so f is sent in f divided by 1. I mean, it's just f divided by 1. Okay, so we have to show the opposite inclusion. So, and so what we will use here is the Nullstellensatz, because somehow it's not an easy fact. One cannot really see it directly, but the Nullstellensatz will allow us to see it. So let me take an element h in OX. We will have to show that we can write it as a restriction of polynomial. So by definition, we can write, so for any point P in X, we can write, say, H equal to F divided by G, where here I mean this is the class in AX of a polynomial. And AX is kx1 to xn divided by the ideal of x, so this is the class there, such that with g of p different from 0. Now basically you want to show that we can, in some sense, reverse the order of the quantifiers here, that we can write in such a way that once and for all the denominator vanishes nowhere. Okay, so this is what we are given. So now I'm writing an ideal, J. The set of polynomials G in kx1 to xn, such that if I take H and multiply it by the class of G in AX, then this is actually an element in AX. So in other words, we take the ideal of all polynomials such that their class can be a denominator of H. So this is clearly an ideal. Because if G lies there, I can multiply G by any polynomial, and this will still be the same. I just write a numerator, denominator. So here H can be written as some F divided by G. If I multiply by something else, by some L, then it's LF divided by LG. So this works, and also works with the sum of two polynomials. And obviously the ideal of X is contained in G. Because if G is in the ideal of X, then H times G will be 0. And that certainly lies in AX. Okay, so we have this. But now, so we have to look at what I've written here. So by the above, we have that the zero set of J intersected X is the empty set. Because what it says here, for every point P in X, I can find the G in this J such that G of P is non-zero. So that means the zero set of J, at least on X, is empty. On the other hand, as the ideal of X is contained in J, it follows that the zero set, so it follows that if this intersection is empty, then also Z of J is empty. We get so after all, this means the other way around, that the Z of J contains. Now that's what you said. Let me see. Maybe it's better not to say anything. So the idea of X is contained in J. So let's see how it works. So that means that X contains the zero set of J. No, because the inclusion of the zero sets is so the ideal of the zero set of the ideal of X is X, and when you take the zero set, it goes the inclusion is the other way around. So we get this. So if the intersection of this thing is empty, then this thing was empty to begin with because it's anyway contained. Okay, so we get that the zero set of J is empty. But now we have the Nullstellensatz. The Nullstellensatz tells us if an ideal has empty zero set, it must be the whole polynomial ring, or to say it simpler, it must contain the element 1. So by the Nullstellensatz, we have that 1 is an element in J. But this precisely says we can choose 1 as a denominator. So thus H is equal to H times 1 is an element with X. Oh, because by definition, J is a set of all polynomials, so that if I multiply by them, I get an element in AX. I can take 1, so H itself lies in. Okay, so this was this funny result. So this tells us that if we look at the fine varieties and look at the regular functions, we have not added anything. So we kind of, if we take maybe an open subset in the fine variety, we get something else, but we generalize AX for fine varieties by doing this. And so in particular, that's not it. Okay. Now we want to do the same thing in the case of quasi-projective varieties. So we want to define what is a rational function, a regular function, and so on. So so here it's not so completely obvious why we need to do this. After all, we have just proven that if we have an affine variety, we haven't added anything. But we will also later want to look at open subsets, and then it's important. But for projective varieties, it somehow must be more important. We want to define some functions on a projective variety, somehow in terms of polynomials, but we certainly cannot take polynomials on X because polynomials are not functions. No? On a projective variety, because if you might take another representative, you get a different result. So therefore, we certainly have to take something else than polynomials, and what we will want to take is quotients of homogeneous polynomials of the same degree. Because if you take a point and put it in a homogeneous polynomial and take another representative, lambda times the coordinates, it gets multiplied by lambda to the degree. If in the denominator you have the same thing, you place the point by lambda to the thing, you get lambda to the d from the numerator, lambda to the d from the denominator, it cancels out, and you will get a well-defined function. So let me carry that out. So definition, so this is now look at regular function. On quasi-projective varieties. So let say X in N be say for the moment a projective variety. And we started the same way as we started today. So let Ix in K x0 to xn be the homogeneous ideal of X. And so we had before defined AX, so we can also deform something. So take the quotient in the same way with AX, we take kx0 to xn divided by Ix. So the homogeneous coordinate ring I write it as Sx, which is just k x0 xn divided by Ix. And as X is a variety, it means Ix is a prime ideal, so it means this is an integral domain. So again, we can form the fraction field. Okay. But it's a little bit more complicated. So we can form the fraction field, that's well defined, it's just f divided by g, but that's not precisely what we want to take. So, definition. So that first, if f is an element in Sx, we say that f is homogeneous of degree d if it has a representative which has degree d. if I can have f equal to f, so this is again the class modulo Ix, with a f in k x0 to xn homogeneous of degree d. So one should note that this is well defined. So obviously you might be able to represent this f in different ways as a representative, in terms of a polynomial, but I claim that at least the fact whether it is homogeneous of degree d or not, this is well defined. So if f is homogeneous, so no, this is well defined. So if f is homogeneous of degree d1 and of degree d2 different from d1, this should not happen, then we can write therefore f is equal to somehow f1 is equal to f2, where fi in k x0 to xn is homogeneous of degree di. So that means that so thus f1 and f2 are the same class, so that difference is 0 in the quotient. So thus f1 minus f2 is an element in the ideal of x. And note that this one has degree. So therefore, and note that we have that f1, so maybe I call this g. So the part of degree d1 of g is f1, and the part of degree d2 is f2. No? So as Ix is a homogeneous ideal, if G lies in Ix, also maybe I would have here this minus. If G lies in the ideal of X, also these two homogeneous components lie in X. So then, thus, as Ix is homogeneous, we have that f1 and f2 both lie in X, so it follows that f is equal to 0. So obviously, so for every non-zero element in Sx, if it can be written as a class of a homogeneous polynomial, this degree of this polynomial is fixed. And so I can say, it makes sense to say that this is S is homogeneous of degree d. So we denote Sx d, the set of all f in Sx whose degree is d. F is homogeneous of degree d. So, and now I want to define the field of rational functions, and this will be a subfield of the quotient field of this. So, the field of rational functions on X is, it's again written as Kx, is the set of all quotients f divided by g in the fraction field of Sx, such that f and g are homogeneous of the same degree. Well, or f is 0, but anyway. F, so if I want to write like this, there exists a D such that f and g are both in this part of degree D. Okay? So a rational function on X is a quotient of two polynomials, but I require them, of the classes of two polynomials, but I require them to be homogeneous of the same degree. And why do I do this? This is because they define, just, I already said it, but note, if, say, f divided by g is an element in Kx, and so P is the point A0 to An in X, then I can say, so I call this, then I can look at the f of A0 to An divided by g of A0 to N. So assuming that j of A0 to N is not 0, this will be the same as f of lambda A0 to lambda An. Yeah, now I have to be a bit more. Because these are homogeneous of the same degree, so if the degree is d, I get lambda to the d out here, lambda to the d out here, and they cancel, so I get the same result. So such an element in Kx, when the denominator is not 0, defines me a well-defined function where the denominator is not 0. Whereas if I just take an element here, this does not define me anything, because you have polynomials of different degrees. If I put another representative of the same point, I get something different. It's not a function, it's not well defined. And if I take a polynomial, it also doesn't define the function. So if I want a function, I have to take a quotient of two polynomials of the same degree. So now, given this, we can repeat everything we just did in the find case. And define the local ring and so on. So, is it the definition? So, the local ring of X at P is just OXP, which is the set of all f divided by g in Kx with g of t different from 0, which just means that you can, if you put a representative here, it will not be 0. Well, you know that g of p actually doesn't make sense, but whether g of p is 0 or not makes sense. I mean, if I write an element in Kx like this, this always means that f and g are considered to be homogeneous of the same degree. This is implicit in writing it like that. And so in particular, if make it explicit, H equal to F divided by G is an element of X, and F can be written as a class of polynomial F, G as a class of polynomial G, I mean in the X, then I can define H of P equal to F of E0 to N divided by G of E0 to N. So obviously I want that G of P is non-zero, where for any representative of P, so for P equal to E0 A. And we can again see that this is well defined. If I take another representative, I get the same result in the same way as in the defined case. But you see, no, this now makes complete sense. This, if I put any representative of P, I get some number here, I get some other number here, and I take the quotient. If I take another representative, this number will be different, this number will also be different, but the quotient will be the same. Okay. So again, OXP is a local ring with maximal ideal. NP, which is just the set, and it's just the set. I could write it as a set of all H in OXP such that H of P is non-zero. Where I told you what that is. And we can again in the same way define regular functions on an open subset. So let U subset X be open. Then the ring of regular functions on U is OU, which is again intersection of all points P in U of the local ring P, where this intersection takes place inside this Kx. And and this prescription here defines for every element in OU a map from U to K. And for H in OU, we get that the map P maps to H of P is defined here, gives a map which I also call H in U for K. And finally, in the same way as before, we see if we have a rational function, it will be a regular function on some open subset of X. Namely, where the union of the complements of all of the zero sets of the possible denominators. So, yeah. Let me just see where am I. Yeah. sorry, but if f h is lambda x, the domain of h what is it? Is again the union of x minus the 0 set of g, where this is the set of all g in k x0 to xn, which are homogeneous, such that we can write h equal to f divided by the class maybe by g. So f and g are homogeneous of the same degree. And I know by definition this is the domain of h, which I write. And we see that h defines a function, a regular function, from the domain of h to this. So that means h is in O of the domain of h. And by definition, this is the biggest open subset. So, where it would be regular. Okay. So much about this. Now we want to show that, maybe I should have also said again, we say that H is defined at P if H lies in OXP, as in the defined case, and obviously the domain of H is equal to the set of all points in P such that H is defined at P. Okay, maybe that's now as a last thing about these functions, I want to show that regular functions are continuous. If I take, if I use the Zariski topology both for a finite projective space and for for k, which I identify with A1 with the Zariski topology. Position. So let x in the n or x in Pn here closed or locally closed, so whatever closed subvariety. So then let U subset X be open and F be regular on U. So OU. Then as a function F from U to K is continuous. As I said, with respect to the Zariski topology on both on source and time. So proof. So, so we can write F equal to H divided by G, where, so maybe I write it as, maybe I write it as the class of H divided by the class of G, where H and G are polynomials, either in kx1 to xn in the affine case, or in kx0 to xn homogeneous of the same degree. So H, G in kx1 to xn, or H, G in kx0 to xn, homogeneous of the same degree. And obviously the denominator G is not 0. The class of G is not 0. And class means here always the class either modulo ideal of x, no, because we have x, or so it's enough to show that if I take, and I'll call this f for some reason, if I take f and restrict it to u minus the zero set of g, so that this is continuous. This is because this is an open subset of U, and the open subsets, as G goes to all possible denominators, are an open cover of U. And if you have a map from a topological space to another, and you have an open cover of the source, such that on each open subset of this cover the map is continuous, then it's continuous. U are an open cover of U. Okay, so we just have to see that it works here. Now we have to remember that we have the Zariski topology. So the closed subsets. So we want to show that this is continuous, so we have to show that the inverse image of every closed subset is closed. So the closed subsets of A1, so of K, which I had identified with A1, are the empty set A1 and the finite subsets. We had seen that this is the topology. Now, the inverse image of the empty set is the empty set, so there's nothing to show. The inverse image of E1 will be the whole thing, so that's also open. There's nothing to show here either. The inverse image of a finite subset is the union of the inverse images of the points. So the only thing to show is that the inverse image of a point is closed. So enough to show. For every element A in K, we have that f to the minus 1 of A. With respect to this map, is closed in U without the zero set of G. No? Okay. So let's just look at it. We have taken these homogeneous representatives and so on. So what is f to the minus 1 of A? This is obviously the set of all P in U minus the zero set of G, such that H of T divided by G of T is equal to A. No? Now G of T is non-zero that we have assumed, so this is equal to I multiply by g of p. So this is just the zero sets. This is just u minus the zero set of p intersected with the zero set of what is it? H minus A times G. No? If I bring this, I multiply by G of P, bring it on the other side, it's this. And this obviously is a closed subset, the zero set of a polynomial, of a homogeneous polynomial. Okay, and so this is closed.
Is the point of restricting our function to this is just to make sure that there is one polynomial g that doesn't vanish on every point, so we fix the representative of the polynomials?
Yeah, that's, obviously one doesn't have to make such a big story, but yeah, just to make it definite, I want to take just one polynomial, then I can write a zero set of one such thing. Obviously, if you have in another open subset for another polynomial, you would have a different such equation. So therefore, it's but at least in this chart, this is. Okay, so much for these rational and regular functions on quasi-projective varieties. Now we want to use this to define morphisms and rational maps. So I want to do it a little bit different than in the notes here, because it saves a little bit of time to do it slightly differently. So let me just say, so morphisms and rational maps. So one of the things, so as you can, so one of the things in algebraic geometry is that there are not very many morphisms, so that is maps which are compatible with the structure, which is both a good thing and a bad thing. So the bad thing is that you want to use these morphisms to study them and to compare them and whatever. And so if there are few such maps, it makes it difficult. On the other hand, once you do have a morphism, so a compatible map between algebraic varieties, it gives you a lot of information. So that's a good thing. So therefore, as there are, however, so few morphisms, so just a map from one to the other, which is compatible with the structure of algebraic variety, one somehow has to find something less than a morphism, and that would be a map which is not defined everywhere. And this comes here very natural because we want to define our morphisms in terms of rational functions, and the map will be defined only when all these rational functions are defined. And so rational map will be just a map which is coordinate-wise given by rational functions, and it will be defined if all the coordinates are defined and whatever. And then a morphism is one where in addition all these coordinate functions are defined. That's how it works in defined case. In projective case, it's slightly more complicated, but it's more or less the same. So let me start first. So we want is first define a rational maps P and X, and it's done by the open arrow to Y between varieties. Say quasi-prime, just mean open subset in the prime variety, and quasi-projective varieties. So just as maps which are coordinate-wise given by rational functions. And then obviously such a No, rational functions are not defined everywhere, so this map will not necessarily be defined everywhere, but a morphism will just be a rational map which is defined everywhere. Okay, so that's the. So here, strangely enough, we start with with maps which are not defined everywhere, which is something that wouldn't mean in differentiability you certainly don't do that. I mean, it's somehow there are very many maps, and so there's no need to take something which is not defined everywhere. But here we do this, and so let me. Let me try to now do this definition. That is my wonderful piece of paper here. So we do this in two steps. First, we define rational maps and then morphisms to AN and to subvarieties of AN. And then we do this from any variety. And then we define morphisms from any variety to subvarieties in projective space, because there's some difference. And then we want to afterwards treat them all in the same definition. Let X be the quasi-affine or quasi-projective variety remember that this means that it's an open subset in the affine variety and open subset in the projective variety. Not empty, yeah, okay. So a rational map phi from X to AN. Again, I use a broken arrow like this. See, it's a rational map. Is just given by an n tuple of rational functions on X. F1, Fn, with Fi in rational functions on X. I should maybe say that if X is quasi-affine or quasi-projective, I had only now told you what Kx is. So if X, if U in X is open, X is affine or projective. So I just define Ku to be Kx. No? So there's no difference. So for a quasi-projective variety, it's just the same. I just define the field of rational functions on an open, non-empty open subset is the same as on the whole thing. Okay, it's just by definition. So therefore, I know what this is. So what is the map? So the domain of this map of phi, I'll just write like this, is just the intersection of the domains of these rational functions. So, therefore, and we say that phi is defined at the point p is P is in the domain. P is defined as P if P is phi in the domain of phi. So rational map is defined when all its coordinate functions are defined. And obviously, this defines us a map. So this defines, thus this defines a map phi from the domain of phi to an, which just sends a point P to f1 of P until fn. So we see that the rational map defines us a map from an open subset of X to an. So if the Y in an is a locally closed subset, it is a quasi-projective subvariety, and phi from X to an, the rational map, we say that it's a rational map to Y, and we say phi from X to Y is a rational map. If the inverse image of Y is an open subset in X. So that means, so if I take if the domain of phi now viewed as a map from X to an, intersected with phi to the -1 of Y is a non-empty open subset of X. This intersection. So there is a, obviously it could be, so once we don't want, it could in principle be that we have here Y, and X somehow gets mapped to something like that, and then there are just a few points. And that's not the rational, that most points of X are not mapped into Y. That we don't want. And this thing, this intersection, will then be called the domain of phi from X and Y. Okay. And we say that as a map from X to Y, phi is defined here. So such a rational map will be called a morphism if it's defined everywhere. So this also in particular would mean that the whole of X is mapped into Y. So a rational map phi from X to Y is called a morphism if the domain of X, so
domain of phi,
of phi is equal to x, and we write then also so phi from x to y is a proper L, because it's an actual map. Clearly, a rational map is always a morphism from an open subset of X. No? The domain of phi is an open subset of X, so a rational map defines a morphism from the domain of X to Y. Note phi from X to Y defines a morphism which are also known by phi from the domain of phi, which is open in X to Y. Okay. This would be okay. So these are our definitions. We call a map, such a rational map, so a morphism we would call an isomorphism if it has an inverse morphism. So if it's projective, it has an inverse. Morphism phi x to y is called an isomorphism if phi is bijective and phi to the minus 1 and y to x is also morphism. Okay. So we can look at the example we already had. We had this curve, the capital cubic C, the zero set of say y squared minus x to the 3 in A2. So then the map, which we had seen, the map t squared, t to the third, from A1 to C, is a bijective morphism. I had defined the inverse map. We had seen the inverse map. So the inverse map phi equal to, if I write coordinates y at x, so y divided by x from C to A1. Well, you can see that this is not, so this is only a rational map. So which sends a pair AB to A B divided by A. So this is, funnily enough, as a map you can define it everywhere by sending 0, 0 to 0, but it's only a rational map because it's not given as a quotient of two polynomials such that the denominator does not vanish at 0. So this is just a rational map, and it has domain of phi equal to C without the point 0, 0, and it gives us an isomorphism of A1 minus 0 to, again, so we have this, in this direction we have this t squared to the third, in the other direction we have this phi, to c without 0, 0. So we see that A1 and C will not be isomorphic. So we say that x and y are isomorphic if there's an isomorphism between them, but they are, these two open subsets, A1 without 0 and C without the point 0, 0 are isomorphic. So we have this map from here to here, which is not an isomorphism, but if we throw away this point here and this point here, it is. Okay, so I should say again, so in this case, x and y are called isomorphic. We can also see that a rational function is nothing else than a rational map to A1, and a regular function is nothing else than a morphism to A1, no? By definition. So note, by definition, a rational function f into x, or quasi-defined quasi-projective variety, is the same as a rational map. But we also put f from x to A1, which is precisely defined on the domain of f. You know, the domain of f as a rational function is the same as the domain of f as a rational map, and a regular function f in O x is the same as a morphism. Again, by our definition. Okay, so we have now I want to, so we had already in the beginning of the section we had defined polynomial maps, which were just maps which were given, you know, from affine varieties to affine varieties, which were just given by n tuples of polynomials, or by n tuples of elements of AX. And so we want to see that if we look at maps between affine varieties, then morphisms are the same as polynomial maps. We haven't gotten anything new. We are just, you know, generalizing these to other cases. So proceed, and for subvarieties x in closed subvarieties. X in AN, Y in AN. The morphisms P and X to Y are the same as the polynomial maps. I mean, it should be clear to you because we have already shown it. Namely, we had said that a morphism is to a subvariety on EM is given by an n tuple of regular functions, so of rational functions which are defined everywhere, which is the same as an n tuple of regular functions, which are regular on the whole of X. But then, if they're regular on the whole of X, it follows that they're elements of AX, and so therefore it's a polynomial function. Okay, so let me just write this. Position let X in the n, Y in to a subvariety, I don't know, write it twice. So morphism P from X to Y is the same as polynomial. And it's just what I said. So I take that phi from X to Y in morphism, then we can write phi as given by an n tuple f1 to fn, where the fi are all regular on the whole of X, because the domain of phi is intersection of the domains of the fi. So each fi must have the whole of X as domain, so they must all lie in OXX with fi in OX of X, which we know is AX. So this means that phi is given by an m tuple of elements in AX, which is the same as given by an m tuple of polynomials. Okay, so there's nothing new. So now I have only 5 minutes, so I'm not quite sure. I just say couple of words, but then I will not, maybe I will finish a bit early, and then another time I will get back to borrowed time. So now we want to do the same thing in for projective varieties. So a rational map from a variety to a projective space is given now by an, if it's projective M space, is given by an m+1 tuple of rational functions. But one has to see that it's an equivalence class of such m+1 tuples, because you can multiply each of them by the same function, which just means by taking a different representative of the point in the image. And then with these things one works in the same way as here, and one gets corresponding results. I will do it properly the next time. Okay, so thank you, and now it's